These are the problems from chapter 19, and the first one I'm going to do reads: the anode positive terminal of an X-ray tube is at a potential of 125 positive 125,000 volts with respect to the cathode negative terminal. A. How much work in joules is done by the electric force when an electron is accelerated from the cathode to the anode? If the electron is initially at rest, what kinetic energy does the electron have when it arrives at the anode? So they want us to figure out what the work is, and the equation we use for that is that the work is defined, respectively negative work going from A to B is defined as either the difference in potential energy and electric potential energy, so EPE, and I should write this a little bit lower, so I'm going to take this off again. So the difference in electric potential energy BA. Here I have to pay attention that when we look at the formula that the indices are turned in such a way, respectively the difference in potential, electric potential, times the charge. Okay, rest is actually pretty much plugging in numbers. WAB equals negative, and what we got here is an electron. Yeah, the anode, how much worse than my electric force? Electron is accelerated, so there we go. I just had to read that again. So minus 1.6 times 10 to the negative 19. Notice the algebra step that I did of putting the negative to the other side, and of course there it is, and the electron charge itself is negative, times the potential difference. Oh, I forgot to write here the index on the electric potential, which is also from B to A, and this is given in this case here as the positive 125,000 volts. And then just plug into the calculator and you're going to come up with a positive number. And the unit is going to be joules. So there we go, and then I guess I could just plug it in and do it myself here, and I'm going to come up with let's see, three significant figures. Actually it's a 1.60 here times, so 2.00 times 10 to the negative 14 joules is the answer. And again, if you look at coulombs times volts, you're going to come up with joules. By the way, this was part A. I'm going to do part B in a moment. This is some X-ray tube. We have the anode here, the positive terminal, and this part here is the cathode, and it's at a 45-degree angle to the cross-section of this bulb here, this evacuated bulb, and we have this huge potential, 125,000 volts, and then the negative electrons are accelerated towards, and what did I just say where the anode is? Whoops. The The anode is this one here. The cathode is over here, which is negative. So the negative electrons are going to go to the positive anode. They hit the anode, and as they hit it, they're being decelerated. And in literature, the word for that is that Bremsstrahlung is produced, literally braking radiation. It's a German word that's also in English literature. So braking radiation is produced with the same energy with which the electron hit here, and that means with this energy here as well. And that braking radiation has the word X-rays. So the electron is going to come out here. It's going to hit that 45-degree target, the positive anode, and the X-rays are going to come out this way, come out of the paper here, because it's a 45-degree angle, so it's kind of like a reflection out of that, and that's how we get the electrons out of that. The 2.00 times 10 to the negative 14 joules is correct, but notice that it's a really small number, and in high energy physics we like to introduce a different kind of unit that makes it really easy to deal with. This one here is basically 125,000 electron volts. It's not a international unit in the sense of being a metric unit, that's what I mean, but it's an accepted unit within the field that abbreviates something, and you can easily see the connection here. You have potential of 125,000 volts, and you get 125,000 electron volts out of it. And then you can see that this one here is the conversion factor between the two. Okay, let's do part B. It's kind of predictable that this will be the same answer. So it says that in part B, if the electron is initially at rest, what kinetic energy does the electron have when it arrives at the anode? Well, when you look at that long equation there for the total energy, there is no rotational energy, there is no gravitational potential energy, there's no elastic potential energy, but it's pretty much electric potential energy as well as kinetic energy. And it boils down to that the kinetic energy that it will achieve at point B, which is the anode. Ooh, how did I do that? There. Is going to be, again, the difference in electric potential energy from, let's see, whoop, did it again, from A to B, and that then is the same 125,000 electron volts respectively, 2.00 10 to the negative 14 joules. Okay, and the next problem says that 2 point charges plus 3.40 microcoulombs and negative 6.10 microcoulombs are separated by 1.20 meters. What is the electric potential midway between them? So here we have one of the charges, call it Q1, at least I try. Q1 equals positive 3.40 microcoulombs, so 10 to the negative 6, and the other one is Q2 equals negative 6.10 microcoulombs, and there's a distance in between these two. We call it R. You can guess why I do that, of 1.20 meters. Okay, and let's see, let me check that. Separate. What is the electric potential midway between them? So what's the electric potential right here? Well, these are point charges, so we have to look at the electric potential due to a point charge, and that is V equals K times Q over the distance R. I have to be, the way I wrote this here, I have to be a little bit careful. Actually, I will take this R away here. And again, you will see in a moment. I actually put it in here because of this R right here. That's why I wrote it. But then I realized, when I do the calculation later, that the actual distance is actually half of that. So I better not call this R here. And then later on, I have R equals, well, half of 1.20 meters. So I better call it that way. Respectively, I better write it that way. Okay, that means that the electric potential midway between these two charges is V equals at 2, so K times Q1 divided by R plus the potential from the other one, K Q2 divided by R. Of course, the second one, the charge is negative, so this one being positive, this one negative, actually they kind of subtract, and this R here is actually the point halfway in between, so that's actually 0.60 meters. R equals, okay, and the K of course is the 8.99 times 10 to the negative 8.99 times 10 to the 9th Newton per Coulomb squared times meter squared, the proportionality constant. And then it's just a matter of plugging in numbers. And when you put all the units together, you would come up with volts. Okay, and the next problem reads, the electric potential energy stored in the capacitor of a defibrillator is 73 joules and the capacitance is 120 microfarad. What is the potential difference across the capacitor plates? So the energy stored for a capacitor is given as 1/2 times the capacitance times volt squared, potential squared, equals, and you come up with something, and because as long as you put them in base units, we're gonna be in joules. The capacitance is given as 120 microfarad. That is actually a huge capacitance. That's why these things are not dangerous. That's why they're so powerful. And and then I just noticed that, of course, the voltage is what has to be determined, and the electric potential energy is given 73 joules. I kind of look over as I record this here over my left shoulder into the book, and then to the right onto my screen, and unfortunately sometimes I miss something like that, but it's easy to correct. So the electric potential energy, therefore, do the algebra on this one here, is 2 times the electric potential energy, divided by the capacitance, take the square root, come up with the electric potential in volts. And I take this one off because I don't need it.